Okay. This morning during the tutorials, so you were doing this problem, okay, and the last part of the problem, we start to be involved to verify that for the smallest non-abelian group, the units, the torsion units are all conjugate to the group elements in the rational group algebra. And so, I mean, the technique that was shown in this exercise is just you basically put your integral group ring in a certain format of matrices, which looks, you can do some linear algebra, but I mean, involved. So you may want to have a better tool for that, and this is what we are going to start to see today. Okay? Something which is more efficient than just basically what we were doing this morning. Basically. Well, before that, yesterday I mentioned several problems. Most of them we know that they have negative solutions for some specific groups, but they have positive solutions for very large classes of groups. But I mentioned two of them: the spectrum problem and the prime graph question, who are still open, so there are no any negative solutions, so maybe they are always true. Maybe they always have positive solution. And I forgot to mention, well, I didn't forget, but I didn't have time to mention one more, well, we call it now the Kimmerle problem. Good that Wolfgang is here today. But I'm not going to mention it now. This will come after some motivation. Okay. Well, the Sasser-Haas conjecture asks whether the torsion units, augmentation 1 of integral group ring of a finite group, are conjugate in the rational group algebra to group elements. And you may ask, why in the rational group algebra? You can consider another bigger field. Okay, so instead of taking rational coefficient, maybe you can not do it over the rationals and you can do it using coefficient on a bigger field. And why? Because it doesn't make any difference. Let me show you why. Take any infinite field. And a finite dimensional of algebra I want to forget the sensible hypothesis. And take a field extension. Okay, and now you blow up the algebra so that you obtain a bigger, now an E algebra, and take M and N finite subsets of A, which are conjugate in B, so in the bigger algebra. Then they are conjugate in A. So they cannot be conjugate in B if they were not already conjugate in A. Okay, I'm only going to give you the hint of the proof, which is the hint is very simple. In the end, that certain conjugacy relation can be rewritten in this form. And this, in the end, is a system of linear equations. Okay, you're in the finite dimensional algebra, so in the end, you have to solve a list of finite. And basically, it says that this system of linear equations have a solution. Well, the unit u that you are looking for is the unknown. Okay, and you can write it in terms of the basis. So in any way, in any case, you have to there is a system of linear equation that has a solution in B, which basically means solution over the field E. If you start with the basis, it's a solution over the field. But it has coefficients because X and Y are inside A. It had coefficient on F. Of course, if a system of linear equation has a solution with coefficient in F, has solutions in F, in a bigger field, it also has a solution in a smaller field because it's a matter of a certain rank of the matrix. Okay? Second part is you have to show that if it has a solution which is a unit on the top, you have a solution which is a unit on the bottom. But here, being a unit means that the norm, when you use the representation, the norm has to be different from 0. Okay? And if it has a solution whose norm is different from 0 in the bigger one, so the norm, which is basically a polynomial, is not the 0 polynomial. Okay? And then it has a solution in an infinite field. The non-zero polynomial has a solution. If you go into the family of solutions, some of them is a root of that polynomial, which is defined by the norm, and this is the proof. This is basically the proof. Okay, so it doesn't make any difference if you make the field bigger. Okay, which means, I mean, when you, instead of the rational group algebra, you want to consider a bigger field like that, this is exactly tensoring over Q with F. If there is a solution here, so there are conjugate here, there are also conjugate. So enlarging the field doesn't make any difference. What about enlarging the group? And this is the Kimmerle problem. No, the field has to be infinite. This is important for a polynomial who is not 0, has always solution in an infinite field. If field were finite, you may have a non-zero polynomial without solutions. That's why you need the F to be infinite. But here we are using only infinite fields, of course. Okay, so the Kimmerle problem is a generalization of the Sassenhaus problem, or the Sassenhaus conjecture. Is to start with is if U is a torsion unit it's a G, a torsion element, is there a group H, finite group, containing G such that U is conjugate in QH to an element of G. So now we know that the Sassenhaus conjecture is false, so the Sassenhaus problem has negative solution for some groups. So if we want to do this with H equals to G, we know that it's not always possible. But the counterexample is not a counterexample it's not a negative solution for this problem. So we don't know any negative solution for this problem. It's open. It may be always true. Okay. Okay, this proposition has some consequences. Okay, one of them is the one I said. Okay, if you have two finite groups, I already said, but I'm going to write it. If you have H a subgroup of this G finite subgroup. And F is a group, is a field containing Q. B red. Okay, if H is conjugate in Fg to a subgroup G, then it is also conjugate QG to a subgroup of. Okay, so this is, I already said, but I wanted to write it. And another one is this one. So take H1 and H2 finite subgroups of this set G. Then H1 and H2 are conjugate in QG if and only if there exists an isomorphism such that I H equals high of phi H for every reducible character of G. Okay. I promise to prove basically most of the things, but all. Well, let's do that. Of course, if there are conjugate, the conjugation is an isomorphism, and conjugates objects has the same character. So one implication is obvious. So we are going to prove the other implication. Okay, for every character, for every reducible character, we fix a representation affording the character high. Okay, so yes, the product of all these representations is an isomorphism from set G to the matrices of a given of the degree, the appropriate degree. Okay, so we have an isomorphism like that. Okay, so an H1 and H2 are finite subgroups here. So if they are conjugate here, if they are conjugated here, if and only if they are conjugated here. But if they are conjugated here, because of this, they are also conjugated over the rational group algebra. Okay, so we need to show that their images here are conjugate. Call this is phi, so let's call this psi. If we prove that the two images are isomorphic, are conjugate here, we have finished. Okay, but what we know is that when we project to every component, okay, so we have I mean, when we project to every component, what we obtain is exactly the representation row. So we have these two representations, okay? And what we have is a certain isomorphism, okay? A certain isomorphism which preserves the character. And this implies that these two groups are conjugate here. So these are conjugate here. The images are conjugate here. Because now this is a direct product, so if in each coordinate things are conjugates, you can take in each coordinate one invertible matrix that maps one to the other, and you put all together, and you have a unit which conjugates one to the other. Okay? Okay, so this is a way, but of course it's not a very efficient way because you need to find this isomorphism which preserves the character. Okay, so still nothing which can be put it in a special case and verify that. Okay, to obtain something more efficient, I need to introduce some notation. And this is for an arbitrary ring. We are going to denote that way the additive subgroup generated by the Lie brackets for X and Y arbitrary elements in R. Okay, this is an additive group. Okay, one thing is that if S is a subring of the center of the ring and R is generated by a certain set as S module, okay, then this is the S module generated by the brackets in the generating set. So it's simple calculation because we write every element as a linear combination with coefficient in S, but the elements in S are central, so you can. So in particular, for a field and a group, this is the F module for a space generated by the brackets of the group elements. Okay, and we will use that later. And okay, yesterday I introduced some notation, this inclusive map, so the partial augmentations, that was when you start with any subset of your group, you define a map from the group ring, arbitrary group ring to ring, simply summing the coefficients in the subset. Okay, and we are going to use this notation, but with some special subsets, actually the conjugacy classes of G. So let's denote this, the set of conjugacy classes of G, and the partial augmentations in a group element of a group ring element are the sets, the maps are the sum of the coefficients with C running in a conjugacy class. Okay? And using these partial augmentations, one can characterize in a different way the Lie bracket of a group ring over a commutative ring. This is formed, well, this is exactly the sum with G and H in G of guys, but it's also the elements having all partial augmentation 0. Okay, if you want to know if a group ring element is in this set, you calculate the partial augmentations and have to check that all the partial augmentation has to be 0. Well, we already know this because I mentioned before. Okay, so this equality is clear that the inclusion because the partial augmentations are linear map. So you only have to check that the partial augmentations of these guys are 0, but of course the partial augmentation of this okay, and of course the partial augmentation of a group element is 1 if the group element is in the conjugacy class and 0 otherwise. Okay? But these two guys are conjugate. This is the inverse HGG. So both are in the same conjugacy class. So if this class is C, this is 1 and this is 1, or minus 1, 0, and if it is not C, this is 0 and this is 0, so this is also 0. Okay, so this gives this inclusion. And to obtain the other inclusion, okay, take any element here, okay, and of course, you write it as a group element, as a group ring element, but I'm going to rewrite it by classifying the group element by conjugacy classes. Okay? But if this element is here, means that the sum of these coefficients is exactly 0. So if I subtract here the sum of these coefficients, and I take for each conjugacy class one representative. I choose one representative and I replace it by this. I'm just subtracting 0 because these sums are all 0. Okay, now I rewrite this in that format. This G in C. G in C of AG, G minus GC, okay? But this is exactly a Lie bracket, because this G is conjugate to, this G is conjugate to GC, because it's in the same conjugacy class, so G is in C, and GC is also in the same conjugacy class. So G minus GC is T inverse GT minus C GC, and this is G inverse G comma T. Okay. So this is G is well, GC T minus GC, and of course this is a linear combination of this kind of function. We have the equality. Okay. Okay, this is going to be useful soon. Well, for example, if S is a subring of R is still a commutative ring, SG, SG is exactly the intersection of this, because it's something which is here, but with all partial augmentation 0, which is, it is here, it has a partial augmentation 0 and vice versa. Okay? This is one thing. The other part? Anyway, I will do it. Another thing is that this is exactly the direct sum like that. Here, T belongs to T, where T is a set of representatives of conjugacy classes. Okay? And G is in the conjugacy class of T and different from T. Okay? So in particular, this tells you that this is a free module of rank, but the number of the group minus the number of the conjugacy classes. This is free rank, the cardinality of the group minus the cardinality of the number of, the cardinality of the set of conjugacy classes. So the quotient is a free R module rank the number of conjugacy classes. Okay? Anyway, so now we are getting close to what we want. Take H, a finite subgroup of units of augmentation 1. And then the following are equivalent. Or the first is that H is conjugate in QG to a subgroup of G. I'm going to give conditions which are equivalent of what we want. Okay? There exists an homomorphism phi from H to G such that for every element in H and G in G, the partial augmentation. Well, I should have said this. So this is an abbreviation. Okay, this is a subset here. But we are going to use it mostly on conjugacy classes. So when I write this means that where this is the conjugacy class containing G. Okay? There is an abbreviation. Okay, so what we have to check is that, well, this condition is that this is 0 for every element which is in G, but not in the conjugacy class of 5H. we observe one thing, which is that of all the partial augmentations, only one is non-zero. This is one of the conditions, and the only condition, basically. Okay? Because only when you calculate the partial augmentation in this conjugacy class, it's not zero, in the others are all zero. Basically, this is the idea. Okay? Okay. I delete the proposition that I want to use. Okay? One implies two. So suppose first that U is conjugate to a subgroup of G with U a unit in the rational group. Okay? This is the assumption 1. Okay? So we take as homomorphism exactly conjugation by U. Okay? It's an homomorphism from H to G. Very good. And H minus phi of H is H minus U inverse HU, which is the Lie bracket. This is this Lie bracket, so this is here. But every element, yeah, because this is in G, and this is in set G. Okay, this has coefficient in set G, so it's in set G, set G. Okay, so in particular, because it's here, the partial augmentations of these two guys are equal. The partial augmentation of this is 0, and the partial augmentation is linear. Okay, but this is a group element. This group element, I mean, in a group element, the partial augmentations are 0 only in the conjugacy class where this element is. Certainly, in the conjugacy class, here, in all the other conjugacy classes, the partial augmentation is 0. This is 0 if G is not in the conjugacy class of phi G, sorry, 1, and 0 otherwise. So it's 0 everywhere. Of course, if all the partial augmentation except for 1 are 0, the partial augmentation in the last one, in the one which we didn't consider, has to be 1, because the total augmentation is 1 and is the sum of all the partial augmentation. All but 1 are 0, so the remaining one has to be 1. And so all the partial augmentations are equal. In the remaining one that we are not checking here, this is 1, and this is the partial augmentation of a group element, okay, where G is in the conjugacy class. So it's 1. So 2 implies 3 is basically obvious. Obvious because the partial augmentation, because of U is 0. Not the partial, the total augmentation is 1. Okay, now we need to prove 3 implies 1. And now is when I'm going to use the result that I proved before, that to check that two groups, torsion units, are conjugate in the rational group algebra, I need an isomorphism which preserves irreducible characters. Remember, this is something that we proved before. Okay, so I'm going to find one isomorphism from H to G to phi of. First of all, I'm going to prove that this phi is injective. Okay. Okay, we have these homomorphisms which satisfy this condition. So suppose that phi of H is 1. Okay? So then what is the partial augmentation in 1 of H? My assumption is the same as the partial augmentation of phi of H, which is 1, so this is 1. So this is a torsion unit whose, what is the partial augmentation in 1? Exactly the coefficient of 1. So the coefficient of 1 of this element is 1, and it's a torsion element. Okay? What the Berman-Hinman theorem tells us? That the torsion element whose first coefficient is non-zero, only 1 or minus 1, but it has to be 1 because the augmentation is 1. So this says that H is 1. So this proves that phi is injective. So phi is an isomorphism from H to phi of H. If I check that it preserves the characters, I finish. Okay? But this guy has all partial augmentation 0, because these two guys has the same partial augmentations everywhere. And the partial augmentation is linear. Okay? So this implies that phi H minus H belongs to the commutator because of that lemma. Okay? Well, the Lie commutator is the sum of commutators of group elements. When you apply and this is GH minus HG. When you apply a character here and here, you get the same. So when you apply a character here, you obtain 0. When you apply a character here, you obtain 0. So this implies that both guys has the same character as we wanted. Okay, great. So we have this proposition which tell us, well, equivalent conditions for two finite subgroups to be rationally conjugate in the rational group. But this is not as good as I would like, because still I need to look for this phi. Okay? But for torsion elements, it's the same for cyclic groups, we can do better. Let's see. This is a theorem proved by Marciniak, Ritter, Segal, and vice. Okay, take a torsion element, unit of augmentation 1, and then the following are equivalent. 1, U is conjugate in QG to an element of G. 2, for every I from 1 to n minus 1. Here, n is the order of U. There exists a unique conjugacy class P of G with partial augmentation different from 0. So all the partial augmentation except for one of them are 0. 3 for every I from 1 to n minus 1, and every conjugacy class of G, the partial augmentation of U to the I is non-negative. Okay? So now we don't need to look for a homomorphism. It's something that you can check in the element. Calculate partial augmentation. Okay? 2 and 3 are obviously equivalent because we are summing, I mean, the total augmentation is 1 and is the sum of the partial augmentations. There are integers. If they sum to 1 and there are non-negative, all of them has to be 0 except for 1, which is 1. Okay? So there is no other way to sum non-negative integers and obtaining 1. Okay? And the other implication is obvious. So this equivalent is clear. And of course, 1 implies 2 is a consequence of the proposition. Because when your unit, and in particular the group generated by this unit, is conjugate to, well, if your unit is conjugate to a group element, the group generated by this unit is conjugate to a subgroup. Okay, and so in the elements, all the partial augmentation has to be 0 except for one of them. Okay, so 1 implies 2, we also know. Okay, so now we need to prove that 2 or 3 implies 1. And what we are going to do is to prove that it implies this condition. So that there exists such an homomorphism satisfying this condition. Okay, but for that I need to prove first a lemma. Take an element here, p prime integer, and x and y elements in the group, such that the partial augmentation of b is 0 for every element which is not in the conjugacy class of x, and partial augmentation of v to the p is 0 for every element which is not in the conjugacy class of y. Then xp and y are conjugate. Observe that x and y are elements in the group, are conjugate in G, in the same conjugacy class. Well, so these are torsion units of augmentation 1, the hypothesis is that the partial augmentation are 0 except in one conjugacy class, this conjugacy class, and also for the v to the p. So in the remaining conjugacy class, the partial augmentation is 1. Okay? So this has the same partial augmentation as x, and this v to the p has the same partial augmentations as y. Okay? Because except in the conjugacy class of x, the partial augmentation are equal and 0, and in the partial augmentation of x, this is 1 and this is 1 then with this one. Okay? Okay. So v minus x has all partial augmentation 0, so it's here, because all the partial augmentation of v minus x is 0, and also v to the p minus y is also here. Okay? And now we need a problem, one of the problems that you have to solve. Okay? Which says that x to the p is congruent. Of course, if x is congruent to v modulo this is a additive subgroup, is congruent to v to the p modulo set g, set g. This is clear because actually they are conjugate modulo this. And also because powers of elements here are also there, pth powers. But this is the problem. Actually, this is problem 11. Okay, so this is something that you should try. Which means that modulo p, these two guys are congruent modulo this. So xp minus vp are congruent modulo set pg set modulo set pg. Okay. We go modulo p and correct. But of course, v to the p is also congruent to 1 modulo this, so it's also v to the p is congruent to y modulo this. So xp and y are equal modulo this Lie commutator in this group ring, which implies that they have the same partial augmentations here. Okay? Of course, the partial augmentation of a group element in a group ring is 0 except in one conjugacy class, the class where it is, where the element is. So these two guys, which have partial augmentation different from 1 in the same conjugacy class. So they are in the same conjugacy class. So they are conjugate in G. Okay? This implies that the partial augmentations of these two guys are equal. And this is one only in the conjugacy class, where then both has to be, and the others are 0. So they are conjugate. Okay, and now I can finish with the proof that 2 implies 3, or 1, or 2 of 1. This only will take a few minutes, 1 minute or 2. Okay, if I finish? It's okay if I finish the proof. So suppose that 2 holds. Okay, we know that that for every power of u to the I, there is exactly one conjugacy class where the partial augmentation is non-zero. Okay? Well, I'm going to denote by GI one element in the group such that the partial augmentation of u to the I is non-zero. Because it's not uniquely defined because there are all the elements in the same conjugacy class satisfy this. But only one conjugacy class, so only in one conjugacy class this happens. So this is well defined up to conjugacy class, but I choose any element. Okay? But observe that if this is non-zero and this is not 1, the Berman-Hillman theorem, this is not 1. Okay? So u to the g sub I is in the conjugacy class of 1, so it's 1, if and only if this guy is 1. By Berman-Hillman, u to the I is 1, if and only if this is 1, 0, sorry, no, different from 0, if and only if gi is 1. Okay, so only from 1 to n minus 1, the only one of the gi's, which is exactly, well, actually, I mean, this is for I from 0, from 1 to n, okay, only if I is n. Okay, for the others, not. And now I am proving that G sub I is conjugate to G1 to the I in G. Okay, for every I. Of course, it's true for I equals 1. And I'm going to argue by induction on the number of primes in the factorization of I. If there are no primes, it's because I is 1, and this is a triviality. So in induction step, I may assume that I is P times J. And my induction hypothesis say that Gj is conjugate to G1J. Okay? And now Gi has the same partial augmentations as Ui because of, this is the election of Gi. Okay? U to the I, sorry. Okay? The same partial augmentations in Gi is 1, in the others are 0. And Gj has the same partial augmentations as u to the j hypothesis also. But Gj is conjugate to this one, so it has also the same partial augmentation as G1 to the j. Okay? And now I apply the lemma for V equals to Ui. U to the I has the same partial augmentations as Gi. U to the j has the same partial augmentation as this. This is this guy to the P. Okay? And this, and therefore Gi is conjugate to G1 to the P in G. By the lemma, Gi is conjugate to G1 to the I in G. So what I prove is what I claim here, but then it says that G1 has order n. Because And it's conjugate to these GIs, and the only one which is 1 is G1 to the n, up to n. So the order of G1 is n. The same as the order of U. So the map G1 to U, mapping G1 to, or the other way, UI to G1I is an isomorphism from the group generated by U to the group generated by G1. But because this guy is conjugate to GI, and GI is the only element which, well, this guy has the same partial augmentations as this. Of course, this guy has the same partial augmentation. So we have the homomorphism phi which satisfies this condition. Or this condition if you want. Isomorphism with the same partial augmentation. And that's it. Okay? So we now have one criteria to decide is some unit, something that you can check simply calculating the partial augmentations. Some element is rationally conjugate to the group element. Okay? Sorry.